I'll begin. Dear Father, we thank you for this day. Thank you for the students. Just ask you to bless this lecture today, Lord. In your name I pray. Amen. All right. So I will state Theorem 9. I think that's a reasonable starting point. Theorem 9 says that if we have a finite subgroup G, sigma 1 is 1, sigma 2, sigma n, a subgroup of the automorphisms on some field K, and let's say F is equal to the fixed field of G, then Theorem 9 says that the degree of K over the fixed field of G is equal to n. All right. And again, the proof is on page 570 to 571. It's rather beautiful, and it's mostly linear algebra. It stems on the notion that independent automorphism, like distinct automorphisms, give you linearly independent. Well, they restrict to linearly independent characters, which is just defined in the run-up to that theorem. Now, that then gives us corollary 10. Corollary 10 says the following. It says K over F, a finite extension. All right, then the size of the automorphism group, which fixes the subgroup of the automorphism group, which fixes F, the F-fixing automorphisms of K, has order at most the degree of the extension K over F. All right. And it says, with equality, if and only if F is the fixed field of ought K over F. Let's see here. I guess that in our other notation would mean that K ought K over F equals F. So the fixed field of, well, son of a gun. Put another way, K over F is Galois if and only if F is the fixed field of ought K over F. All right. I think we can look at the proof of corollary 10. That one's not too bad. Let's try to look at it. All right. Here's the proof. He says let F1 be the fixed field of ought K over F, right? So that we have F is a subset of F1 is a subset of K. All right. So then by Theorem 9, what do we get? He says by Theorem 9, the degree of K over the fixed field, right, is equal to the order of the automorphism group of K fixing F. But then what else do we have here? What's this say? This says that we can look at the degree of K over F as what? The product of the degree of what? K over F1 and F1 over F, right? So if this one right here is order ought K over F, right? If those are equal, right? By Theorem 9, that implies that the then this has to be, if this is 1, right? If F happens to be the fixed field, I mean, you can see the equality also, right? If F1 is equal to F, then we get this is equal to that, which is part of the corollary with equality. Otherwise, the degree of the automorphism, the KF fixing automorphism. Man, I need to find something less annoying to say. That's like so much. Every time I say that, just so much to say. This. Sorry. Anyway, there you go. That's corollary 10. Okay, corollary 11. Corollary 11 says what? It says if G is a finite subgroup of the automorphisms of a field K, all right, and F is the fixed field of G, then every automorphism of K fixing F is contained in G. That is to say that ought K over F is equal to G. Thus, K over F is Galois. With Galois group G. Let's see here. Is that clear? G is a subgroup of the automorphisms. F is the fixed field of G. Okay. Now, let's see here. Here's the proof. Anyway, I'll the proof with you here. He says, by definition, F is fixed by all elements of G. You know, if sigma is in G, then sigma of x is equal to x for all x in F, right? That's because x is the fixed field of G, right? So then what? He says that means that G is a subgroup of the F fixing automorphisms of K. So we're trying to show equality. What do we need to do then? Yeah.
Is there a difference between when you write Galois in like small caps?
No, no.
No, okay.
No.
Is that like your notation for something, or is that just sometimes it happens?
What do you mean?
Like sometimes you write Galois in like all caps.
Oh, I just like the way all caps looks.
Okay.
No,
Sure
it's
like
not.
something.
It's not a thing. No, no. It's not. It's no thing. Okay, so the question is, what about the other way? So this gives us that G is a subset of ought K over F, right? We're claiming that in this context that they're equal, so we should do what? Yeah. He says, of course, this also tells us what? That the order of G, right, is less than or equal to the order of ought K over F. Was it? What was I saying about class not being distracted by convocation? I forgot about the... Man, imagine if you were teaching at the other end of the hallway right now. Because that noise is from the big blue room.
Wait, are you sure?
I bet it is. It's not? Is it from right next?
I think it is. They had tables set up in the lunch room. They had tables set up.
Oh, you're right.
It's from next door.
It's from next door. Oh, okay. All right.
But I had a class in the last room in this hallway
Uh-huh.
when there was stuff happening in the grandma. It was so loud, you could barely hear Dr. Wayne.
Yeah, I have raised a ruckus about this before. Okay, anyway, the point is G is a finite set, right? And it is a subset of ought K over F. And since we're in this context, if we could prove that the size of G was the same as the size of ought K over F, we'd be done, right? And so I think that's what's the next part of the proof. He says, by the theorem, which theorem? You guys tell me which theorem. By the theorem, we have that the order of G is equal to the degree of K over F. Which theorem is he referencing here? Theorem 9, right. So by Theorem 9, and what else? And corollary 10, what do we get? We have that the size of G is what? Greater than or equal to the, what is it? Oh, ought K over F. Thank you. I'm too close to it. And so therefore, the orders are equal. And since we're dealing with finite groups, you have a subset of a finite group, or you have a subset of a finite set which has the same size as the set, they're equal. So that's where the finiteness is important. All right, that's corollary 11. Corollary 12. Corollary 12. If G1 is not equal to G2, and G1, G2 are subsets of some group of automorphisms of a field K, then guess what? KG1 is not equal to KG2. So the fixed fields corresponding to subgroups G1 and G2 are also distinct. All right? And the proof is by contradiction in what's given above. Okay, I won't even write it out. What he says now is, he says, by the corollaries above, we see that taking the fixed fields of distinct finite subgroups of automorphisms of K give distinct subfields of K, over which K is Galois. Further, the degrees of the extensions are given by the orders of the subgroups. Maybe we should just like go over to like, we should just meet at like, I don't know, what's that place over off, over by Home Depot? No, not, well, La Coretta.
That's by Lowe's.
But, yeah, there's no,
Are you talking about that really, really expensive, like, wedding venue?
no. I was thinking that place where they, with the loud music and the skating. Fun, yeah, we should just go have class there. It's at least there. If I went there, I would be expecting a constant, constant distraction. I would be prepared for it.
Class field trip.
Okay. All right. Finally. So, Theorem 13, the extension K over F is Galois if and only if K is the splitting field of some separable polynomial over F. Furthermore, if this is the case, then every irreducible polynomial with coefficients in F which has a root in K is separable and has all of its roots in K. So in particular, K over F is a separable extension. So, furthermore, if this is the case, every irreducible polynomial with coefficients which has a root in K is separable. And has all its roots in K. He says, now the proof of this is about a page, and I think it's worth trying to go through, so if I haven't wasted all my time complaining about distractions too much. Debatable. Let's try to at least go through part of the proof of this, Theorem 13, yeah. So I'm trying to pick at the proofs which I feel like involve the concepts of this part of the course and not some sort of technical background. Like Theorem 9 is really, I love the proof of it, but it's not really what the heart concept of what we're at here is about, I don't think. I think it's more of a technical preliminary. Okay, so proof of this Theorem 13, proposition 5, he says, proves that the splitting field of a separable polynomial is Galois. Proposition 5 proves splitting field of separable, what did I just say? Splitting field of a separable polynomial is Galois. Can you guys break that down for me? What's that mean? What's this sentence mean? We're trying to do an if and only if proof, right? So this is the what? This would be, yeah, this would be this direction, right? So what he's saying to start with is that's already taken care of by proposition 5. Is that seem reasonable to you, what was a splitting field of a separable polynomial? Right. All of the roots are in this. All of the roots are in the field. And what else? There's no repeated roots. That's separable, right? The smallest one over which it splits, also true. What does it mean to be Galois? Remember, that means that the degree of k over f is equal to the order of the f-fixing automorphisms of k, right? In which case, we call this the so-called Galois group of the extension, right? So proposition 5 gave us that the degree of the splitting field of an nth order polynomial, right, of a separable polynomial was n. Am I right? The degree of the splitting field of a separable polynomial of order n is n. Is that what proposition 5 said? You don't have uh-huh. It was indeed less than or equal to, but the follow-up sentence is where the goodness is with equality if f of x is separable over f. So that is what proposition 5 says, yes. So it is, proposition 5 literally says this in this context. All right, other direction. So what are we going to assume? Assume that the extension k over f is Galois, right? And then what do we need to do? Yes, right. Exactly. So assume that k over f has the degree of the extension is equal to the order of the group of f-fixing automorphisms, right? And let's suppose that that's equal to n for the sake of discussion. All right? Remember that a Galois extension is finite in here to start with. Okay, so picked up the wrong page. Not helpful. He says, we now show that k over f is Galois, that if k over f is Galois, then every irreducible polynomial in P of x having a root in k splits completely in k. So he says set g equal to the, so he says this is g, all right? And he says let alpha be so also and what else? That's what I was wondering. Let's see. Oh. Okay. Sorry. Now, he's like, assume this is that. I should be more careful. He says, we now show that if k over f is Galois, then every irreducible polynomial. All right, so if f of x in f of x is irreducible and f of alpha equals to 0 for some alpha in K. All right? Then f of x splits in K. All right. So we're going to let alpha be that root of the polynomial of oh, and he says p of x. All right, p of x. Great. He says also he's going to let g equal to 1 equals to sigma 1 and then sigma 2 sigma n like we did before. You know, like enumerate the automorphisms that are in G. So if you use those, you can say, consider the following elements of K. Namely alpha, and then sigma 2 of alpha, and all the way on down, right? So we're looking at what the Galois group does to the root. We're going to argue that, well, of course, these are elements of K, right? Because sigma 1 through sigma n are automorphisms of K, so they map K to K, right? So to start with, this is a list of K elements, okay? Yeah, sorry. And he calls this equation 14.9. All right. And then what he does is he says, then he says from this obtain alpha 1, alpha 2, alpha r distinct elements of K. So if there are any redundancies, eliminate them. All right, so select a distinct subset, a maximal distinct subset, all right, I think. As he says, the distinct elements in 9. He says, okay, well, if tau is in G, then since G is a group, the elements, so he says tau in G, then if we look at tau alpha, tau alpha 2, tau alpha, tau alpha n, what is that? Oh, I'm butchering it. I'm sorry. That's not what I'm looking at. He said, sorry guys. If tau is another element of G, then we can look at G as, we can also write G as what? We can write G as tau sigma 1, sigma 2 rather, tau, well, sigma 3, I suppose, tau sigma n. He says these are the same elements as 1 through sigma n in some order, right? He says, therefore, it follows that applying tau in G to the elements in equation 9 simply permutes them, right? So in particular, applying tau to alpha 2, alpha 3 to alpha r permutes the elements. Right? So, in other words, this is just equal to, do you understand what he's saying? So if I call this whole set here, let me just put a set around it if you don't mind. This is a subset of K. Let's call it S. He's arguing that tau of S is just equal to S again, because tau is what? I mean, if you let tau act on these things, it's just these things again out of order, right? So that just gives us back the set again. What does that mean? Well, tau is just an arbitrary thing in our Galois group. But this shows that the original root and all of the roots which it generates through the Galois group, sigma 2 of alpha, sigma n of alpha, those are all fixed. I mean, well, not individually, but as a set, right? Well, here, let's see if you believe this. He says it follows that the polynomial f of x equal to x minus alpha, x minus alpha 2, x minus alpha r has coefficients which are fixed by all the elements of G. I think about it this way. So if I hit this with a permutation in the Galois group, what it does is it kind of just permutes the factors. Essentially, what happens. Stupid example would be like this. You got, x plus I times x minus I. You hit this with complex conjugation. What happens? Let tau be complex conjugation. What does it do? Right? It just permutes the roots. This is saying that happens in general with the Galois group, if we sort through this argument. All right. He says, hence the coefficients lie in the fixed field of G, which by corollary 10 is the field F. Hence, f of x is in. So this implies that f of x is an element of f of x where f is equal to the fixed field of G. Next he says, since p of x is irreducible and has alpha as a root, p of x is the minimal polynomial for alpha over f. Hence divides any polynomial with coefficients in f which has alpha as a root. This is from chapter 13. He says it follows that p of x divides f of x in big F of x. Since obviously f of x follows, obviously f of x divides that. In k of x, we have that p of x is equal to f of x. In particular, this shows that p of x is separable and that all of its roots lie in k. In fact, they are among the elements alpha, sigma 2 alpha, sigma n alpha, proving the last statement of the theorem. And then he has a paragraph to prove the last part of the theorem. Which I think is the abstract version of what I wrote on the board last time concerning taking repeated roots, like a repeated part, and getting rid of it to get the underlying irreducible polynomial. Remember we looked at that? The next paragraph is essentially the abstract version of that. Now, this brings us to a definition. And yep. Yeah, go for it.
We have p of x written on the top line.
Yeah.
And then that's the only time it happens. So
Well, the paragraph that I read but didn't write down proves that P of x is equal to f of x.
So on the top line, that f alpha is f, not p. And same with the thing after it.
No, that's supposed to be a P. That's supposed to be P. He doesn't even write that down. I wrote that down.
And then the same for the other one on that line also? Where it says f of
Yeah,
x?
yeah. I mean, this is, I think, this is what we're trying to prove, right? I mean, this is bad. You know, I mean, I shouldn't even write this here, right? This is what we're trying to prove. We've assumed that the extension's Galois. We're trying to prove that an irreducible polynomial splits completely. I think. Oh. Well. No, this sentence at the start of page 573, it is saying what he's going to do over the next paragraph. It's a statement. He says, we now show this. So it's not, this is not given to us.
But that's what we're trying to show.
So we're trying to show.
Okay.
So perhaps I should just erase this and go from there. At the end of this, by the paragraph I didn't write down, he argues that f of x is equal to p of x, using a little argument about the minimal polynomial and the fact that one divides the other and so forth. All right. Oh, well. Oh, well, oh, well. Definition. K over F Galois. If alpha is an element of K, then the elements sigma alpha for sigma in the Galois group of K over F are called the conjugates, or if you like, Galois conjugates of alpha over F. If E is a subfield of K containing F, the field sigma of E is called the what? Is the conjugate field. It is a conjugate field of E over F. He says the proof of the theorem that I just butchered, well, I showed you part of anyway, it shows what? It shows that the Galois extension K over, that in a Galois extension K over F, the other roots of the minimal polynomial, all right, over F, of any element alpha of K are precisely the distinct conjugates of alpha under the Galois group K over F. And also, the second statement of the theorem shows that K is not Galois over F if we can't find even one irreducible polynomial over f having a root in k, but not having all of its roots in k. Right? So an extension field will not, is definitely not Galois if there exists an irreducible polynomial which takes a root in the extension, but doesn't give you all of its roots in the extension. If you can find one polynomial like that, game over, that's not a Galois extension. That should be familiar to you. The example we keep coming back to, because it's a good example, is what? Exactly. So Q adjoin the cube root of 2, right? Which, like you said, is up to isomorphism Q of x mod Langle, x cubed minus 2 Wrangle, right? That field, here we have f of x in Q of x, right? Irreducible, right? Why is it irreducible? As we've said many times, Eisenstein, p equal 2, right? Yet, zeta 3 cube root of 2 and zeta 3 squared times the cube root of 2 are not an element of this extension over Q, right? And yet, they have to be, because those are the other roots of this irreducible polynomial. So that shows you that, Q adjoin the cube root of 2 over Q is not Galois. Which, of course, we have said before, right? But now I'm starting to say it with all of the full statement of the theory, right? There is more. So at the top of page 574, he gives a list of 4 characterizations of what it means for an extension to be Galois. All right, so what are the 4 ways of characterizations of Galois K over F? He says, splitting fields of separable polynomials over F. He says, 2, fields where F is precisely the set of elements fixed by ought K over F. So in other words, F is equal to K to the ought K over F. 3, the degree, and this was our definition of Galois, right? The degree of K over F was equal to the degree of the F fixing automorphisms of K. And then 4, which we haven't really talked about yet, finite, normal, and separable extensions. So the following are equivalent, all right? For extension K over F. So when we're looking for a Galois extension, we're looking for a splitting field. We're looking for, yeah.
For the last time, that's something that passes all 3 of those things, right?
Yes. Yeah. Finite's not enough. I mean, my example above is finite, but certainly not Galois. And then, on page 574, we have the fundamental theorem of Galois theory. All right. But rather than writing that down, I'm going to go over here, and I want to start referencing a little bit more about Keith Conrad's wonderful blurb called the Galois Correspondence. He, and I just want to draw your attention to where the dictionary between these 2 resources, all right? In particular, in the Galois Correspondence by Conrad, this is his theorem 4.1. All right, this is his theorem 4.1. His numbering is a little bit different. For him, number 3 is number 1. Number 2 is, number 2 is number 2. Fixed point in the dictionary, what do you know? The splitting field statement is number 4 rather than number 1. And his separable normal is number, anyway, who cares? The point is it's the same stupid theorem. There's 4 points and they're the same things, just read it in a different order, all right? And also, if you read the Galois correspondence, you'll find out what separable and normal means. Like he has a very nice discussion of what he means by normal. All right. I think that's also in, it's also in Thumb and Foot, of course, and maybe we'll come back to that as needed. But I should at least state the fundamental theorem of Galois theory today, right? So let's do it. So here is theorem 5.6. I like the way that Conrad states it because it's just a little bit crisper. Theorem 5.6. He says, let L over K be a finite Galois extension all right, with G equal to the Galois group of L over K. Then the inclusion reversing mappings F wiggle, 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 to gal L over F and H, wiggle, 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 L upper H, between the intermediate fields K and L and the subgroups of G are inverses of each other. They're inverses of each other. And using the notation, F equals to L upper H, and H equal to the Galois group of L over F, we have the following. A, number H. What do you think number H means? Yep, the size, the order of the group. Good grief. So then F, the size of F over K is equal to the degree of G over H. Oh, wait a minute. This is interesting. That's actually very interesting what this says. And B, two intermediate fields F and F prime with subgroups H and H prime, all right, are isomorphic over K if and only if H and H prime are conjugate subgroups of G. And he says more. In particular, he says that the Galois group of L mod the conjugate field by sigma of F is equal to the conjugate of the Galois group of L over F by sigma, conjugating by sigma, so sigma, sigma inverse like that. And that's for sigma and G. And then C, and this is what we're going to try to be digesting over the next few days, F over K is Galois if and only if H is normal in G. In which case, the restriction map G to the Galois group of F over K, where sigma maps to the restriction of sigma to F, is surjective with kernel H. So, I'll just get to the point here. G over H is, in fact, isomorphic to the Galois group of F over K. So, let me just throw up, unfortunate choice of words. Can you guys help me out? What's the lattice diagram for the splitting field? If we look at L equal to Q adjoin, was it rho and the cube root of 2? This is a splitting field for x cubed minus 2, right? And that has various subfields, right? One of the subfields it has was Q adjoin rho, right? And then it also had, what were the other two? That has degree what? That has degree, stink. Yeah, that's degree 2 over, that one itself is degree 2 over Q, right? And this is degree 3, I think. I mean, I know that's a degree 6, but there's 3 other. There's 3 other. Come on, you. So I'm trying to find my picture. That's the other nice thing about the Galois Correspondence by Conrad. He has many more pictures of the things we're doing right now than Dummett and Foote does even. See if I can find it right quick. I mean, I saw it just a second ago, but I forget where I put the stupid thing. Oh, well, this is a partial picture. It's not a complete picture, but he uses omega rather than rho on page 13 of the Galois Correspondence. And anyway, there's also a Q adjoin the cube root of 2 field over here, right? We were just talking about how that is degree 3, right, over Q, and it's not Galois. But there's other things, right? If we do the other way around, what did we say that the Galois group of this was? We worked out last time, remember? G is, what was it? It was sigma tau, right? And so up here you have the subgroup generated by sigma. And you've also got, like tau. You've got your tau sigma. And you've got your tau sigma squared. These are other subgroups of S3. What subgroup? This is the subgroup of order 3 in S3, right? So only one of these subgroups is normal. What does it take to have, well, if the index of a subgroup is 2, it's normal, right? So what's the index of this? This is 1 sigma sigma squared, right? This is a normal subgroup. The corresponding, what's the fixed field of this? The fixed field of this is Q adjoin rho. Q adjoin rho is Galois over Q. Q adjoin root 3 over 2 is not Galois over Q because this, one of these guys, which one of these has that as its fixed field? Tau. This is not a normal subgroup of S3. It is not closed under conjugation by S3. If you conjugate this subgroup, you can get to this one or that one. And there are 2 other fields that I haven't written here, which are what? Q adjoin something, Q adjoin something else. I forget what to put there. But those are not Galois because these are not normal. So we can discover whether or not subfields of a given splitting field are themselves Galois by studying the corresponding question of the normality of the subgroups which take those as fixed fields. This is the Galois correspondence. Hey, I managed to say something today. Woohoo! Anyway, that's where we are. Now, the other reason you should read the Galois correspondence by Conrad is it literally has solutions to some of your homework problems because I took them directly from here. One important exercise for you, here's a very easy exercise, not collected, but it would help you. I wrote this theorem down, right, from Conrad's. In what way does Dummett and Foote use K? Yes. Right. Notice the... So it might be informative to try to just be aware that they're used in a different sense, okay? We need to think through the ideas, not be a slave to the notation. So anyway, thanks guys. Have a good weekend.